Hello, everyone.
Hello, Professor.
Hey, how are you?
Excellent. How about you?
I'm doing good. So, this is the review session for the final exam. And the final exam will have 4 questions. The first question will be only one part with the short answer, one part. And then the second question will be 6 parts. The third question will be 5 parts. And the fourth question is 5 parts, like A, B, C, D, and so on. It doesn't take much time. I know the exam is 2 hours, but you will see you can finish it in only 1 hour. So it doesn't take much time. And so do not feel like, oh, the exam will be long because it's second question is 6 parts and third question 5 parts, and it doesn't take much time. Okay. Do you have any question about the exam?
No, for the moment.
Okay.
Can it be take home online? It's not too late yet.
It's too late. Because of fairness, all of you should take it in class.
Well, life is not fair, so just make us do it at home.
But I cannot take my decision now. So
Fair.
and believe me, the in-class exams are easier than the take-home exams.
Understand.
Because in-class exam, it means it is limited time, so the professor should write an exam that can be finished in only at maximum 2 hours. But take-home exam, like the professor should write, some questions are hard questions, so they need more time to think about and these kind of things. So the in-class is much better than the take-home exam. But I know the stress is different. The in-class exams is you have some kind of stress, but the take-home exams do not have that much stress, but it's not easier. Okay. The exam will cover chapter 8, chapter 14, and chapter 15. Only 3 chapters. Okay, and it is allowed to have a formula sheet. And don't forget to bring a calculator. Any calculator works fine. The simple one or advanced one, it's up to you. Okay, any questions? And I uploaded guidelines for the final exam. And uploaded the key answer for homework 7. Okay. Okay, so if you do not have any question, I will go over the 3 chapters. And while I'm going over these 3 chapters, if you have any question, stop me at any time. 1 second. What is this? Did they change the Zoom? They updated something? I asked it for. I asked it for the whiteboard. Okay, the classic one. Yes. So do you see the whiteboard?
Yep.
Okay, great. So as I said, exam will cover chapter 8, chapter 14, and chapter 15. So let me go over the first chapter, chapter 8. Chapter 8 is 2 to the power k, fractional, factorial design. So the original design is 2 to the power k factorial design. So the number of treatments is 2 to the power k. But because we do not have enough resources, we are not able to test 2 to the power k treatments. So you can test only 1/2 of the 2 to the power k treatments or 1/4 of the 2 to the power k treatments. So you save much resources. So the goal of this fractional factorial is saving resources, and also some people use it as some kind of screening the explanatory variables or the treatment factors, because you need to know which treatment factors are significant, which ones are not significant. You don't care about the interaction. So you can use 2 to the power k fractional factorial design. So for example, if I have 3 treatment factors, A, B, and C, each has 2 levels, like plus, minus, plus, minus, plus, minus. So in this case, I can write all the combinations or all the treatments in this experiment, which is 2 to the power 3 factorial design. In this case, we have 8 treatments, 2 times 2 times 2. And the design matrix is A, B, C, minus, 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 plus, minus, 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 plus, minus, 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 plus, 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 minus, and the plus, minus, plus, minus, plus, 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 plus. We call the first treatment 1 because all of them are low. Second treatment is A because only A is high, and then B, C, AB, and then AC, then BC, then all of them are high, so ABC. So the number of treatments we have is 8. 1, 2, 3, 4, 5, 6, 7, 8. You can call them T1, T2, T3, T4, T5, T6, T7, T8, but it's better to give this notation because this notation represent, because once you know the treatment A, it means A is high, B is low, C is low, and so on. So if you have much resources, you can test all these 8 treatments, but sometimes you do not have much resources. You have to test only 4 out of these 8 treatments. So how do I select 4 out of 8? You can select 1/2 of the treatments, 1/2 of, or 1/2 fractional factorial design, using the defining relation I equal A, B, C, D, or the defining relation I equal minus A, B, C, D. So you need to have a column A, B, C, D, the interaction A, B, sorry, I'm working with only A, B, C. So we do not have D. So let's have the interaction, the highest order of interaction, which is A, B, C. If you multiply minus times the minus times the minus gave me minus. If you multiply plus times the minus times the minus gave me plus, and then gave me plus, and then plus, and then minus, 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 plus. If you use this defining relation, you select the halves that the column ABC has pluses. So I will select this treatment, this treatment, this treatment, and this treatment. So I will test only these 4 based on this defining relation. But if you select this defining relation, you select the other half. So which one I should select? Either is fine. You can select the halves that I equal ABC or I equal minus ABC.
I have a quick question if that's okay.
Sure.
Sorry, could you explain again, basically with the aliasing where we have the I is equal to ABC?
Yeah, I
Are
will
you
explain the aliases because this is the next step. Once
So,
you know, okay, go ahead.
sorry, so basically it's like, what if you don't have the column that shows the positive and the minuses of the effects?
You have to have these columns because
Okay.
once I give the treatments like 1, you know all of them are minus. A means A is only plus and others are minus and so on. Because these combinations are the treatments. If you have 3 treatment factors, you need to write down the combination of all the 3, all the combinations like minus, 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 and so on. See my point?
Okay, got it. Thank you.
Okay. Because once you know how many treatment factors you have, each has 2 levels, you can write down the design matrix. And then you select the halves that ABC is the highest order of reaction is positive or the highest order of reaction is negative. And then you need to find all the aliases. What do you mean by finding all the aliases? Because testing only 4 treatments and measuring the response only 4 times, you do not have much information, you do not have much observations, you do not have much data to estimate all the main effect and reaction effect. Some of them will be confounded with each other or alias with each other. So you need to find the aliases. How do I find the aliases? You use the defining relation. So if you use I equal ABC and you multiply both sides by A, you get A equal BC because A times I is A times A is A squared is I times BC is BC. And then B equal AC, and then C equal AB. And then if I multiply it by AB, I get C. So this one is repeated. So those are the aliases. What do you mean by those are the aliases? I mean, if you estimated A, it will be the same estimation of BC. If you estimated B, the value of the estimation of B is the same the value of the estimation of the interaction AC. How do I estimate A or B or C? You use the idea of pluses and minuses because you have the response variable, you have these values for only the positive. So when you use this only because you select half. For A, you have 2 pluses. This one is plus, this one is plus. So the average of these two, this one plus this one divided by 2, minus the average of the minuses, the average of the minus is this one. Which one? This one. And you have some, where are these values? 1, 2, 3, 4. And I is plus, minus, minus. So again, the average of pluses is the average of these values of pluses, like this value and these values. So this value divided by plus this value divided by 2, minus the average of minuses, the average of these 2 pluses. So the average of these 2 values.
So a quick question, if it's okay as well.
Sure.
Sorry. Why did we not include the C treatment?
You mean this one?
Yeah.
I included this one, but I did a mistake. Let me.
Because we circle the blocking one treatment, but then
Okay, let me remove this one.
Yeah.
This
I'm
one.
just a bit confused.
Yeah, it's fine. Let's do
Oh,
it.
because I see.
Okay, so now I select this one. It should be minus. And also let me remove this one. This one is plus. Well, this. I'm not good with this one plus. Okay, you selected A, B, C, A, B, C treatments to test. And you measured the response under these 4 values. And 1, 2, 3, 4. When you look at the column of A, you will find 2 of them are positive, 2 of them are negative.
Okay.
So this one is positive, this one is negative, this one is negative, this one is positive. 2 positive, 2 negative. So you get the average of positive minus the average of negative, you get the main effect of A. Do the same thing for B. You will find 2 are positive, 2 are negative. Do the main effect of C. 2 are positive, 2 are negative. So you estimate the main effect of A, main effect of B, main effect of C. But keep in your mind, those three estimates are the same estimation of the interaction between BC, AC, AB. So now I have 3 estimates. I need to know which one should be included in the ANOVA table, because the problem is you have 3-degree freedom and you estimate the 3 effects, but you need to remove at least one of these effects to gain 1-degree freedom to estimate sigma square. So you need to go to the normal, you need to estimate A, estimate B, estimate C, and then go to the normal probability plot and remove the ones are very close to the straight line and keep the ones are far away from the straight line. Maybe when I graph these 3, I will find this one is A, this one is B, this one is C. So I will include on the ANOVA table only A in the ANOVA table. But we covered the more than normal probability plot criteria. We covered normal probability plot, Pareto plot, reference plot, have normal probability plot. But most of the time, those guys will give you the same recommendation. It recommends which estimate should be included in the ANOVA table, which one should not be included in the ANOVA table. So in the fractional factorial design, the first step, select a defining relation. And based on this defining relation, you select half of the treatments, test the half of the treatment, measure the response, and then find the aliases, and then estimate the effect that at the left-hand side, this one, this one, this one, and then go to normal probability plot or Pareto plot or reference plot or have normal probability plot. It will recommend which one should be included in the ANOVA table, which one should be removed from the ANOVA table. And I need to remove at least one, because I need to estimate sigma square, because the ANOVA table will not be able, you will not be able to complete the ANOVA table unless you have at least 1-degree freedom for estimating sigma square. So you get F values, you get P values, and then you can test the effects. Okay, any questions so far?
Why do we use the Pareto plot before the ANOVA table again?
Okay, you use normal probability plot or have normal probability plot or Pareto plot or reference plot to because you need to remove at least one of the effects to gain some degree freedom to estimate sigma square. Those methods will recommend some of them will be removed, some of them will be in the ANOVA table. Like this is normal probability plot. If anything far away from the straight line, this one will be included in the ANOVA table. Anything very close to the straight line, this one will be removed from the ANOVA table. So when I remove the 2 effects from the ANOVA table, I will gain 2-degree freedom. So these 2-degree freedoms will be used to estimate sigma square. So if I am able to estimate sigma square, I will be able to find the F values because I divide by the MSE. And then I get P values, and then I will be able to test this one. Again, the Pareto plot, reference plot, normal probability plot, have normal probability plot, all these ones are statistical methods that can be used to remove at least one of the effects. Because I will not be able to test these 3, all of them. Why? Because I have only 3-degree freedom. I need to save 1-degree freedom for estimating sigma square. So how do I gain 1-degree freedom? How do I save 1-degree freedom? You go to normal probability plot, Pareto plot, reference plot, or have normal probability plot. Does it answer your question?
Yeah, thank you.
You are welcome. And then the last step, don't forget the 3 assumptions again. Independence, constant variance, normality. We always test those 3 guys. So this is fractional factorial design. This is 1/2 fractional factorial design. And there is something called resolution. There are 3 types of resolutions. Resolution 3, resolution 4, resolution 5. How do I know that my design has a resolution 3 or 4 or 5? Each resolution has some characteristics. Once you write down all the aliases, you will be able to know your design is resolution 3 or 4 or 5. Like when you look at these designs, the main effects are not alias with the main effects. They are alias with the two-way interaction. And the two-way interaction are not alias with each other. They are alias with the main effects and so on. So after you go ahead.
Sorry, I'm on the side. I have a lot of questions on this unit and I want to make sure I understand things.
Yeah, sure.
So basically the whole premise of a half of like a half fractional factorial design is you're limited in terms of degree of freedom. You use some type of defining relation, and then you use stuff like the half normal plot to be able to like eliminate anything that would be insignificant, and that can help you save on more degrees of freedom.
Very good.
Okay. You know, okay, never mind. I was gonna ask for a scenario, but it's not gonna be on the exam, so I can ask for that later.
Okay. Any other question, guys?
Just to clarify,
Sure.
the main effect of A, is it average of pluses minus average of minuses?
Very good.
Okay, thanks.
And you don't need to memorize a formula. Like, see how many values you added, divide by the total number. Like, if I sum 3 values, I divide by 3. If I sum 4 values, I divide by 4. You don't need to memorize some formula.
Okay, thanks.
You're welcome. Any other questions? Okay. And then we can use 1/4 is not 1/2. You can use 1/4, but it will be a little bit more work. Like you can use 1/4 fractional factorial. If you use 1/4 fractional factorial, you need to have 2 defining relation. It's not only one. Like if I have treatment factors A, B, C, D, E, F. In this case, how many treatments we have? 2 to the power 6. 2 to the power 6, how many treatments? Is 8 times 8, 64. It's too much. I cannot test the 64 treatments. So, okay, can you test 32? No, I do not have resources to test 32. Okay, can you test 18? Like, let me make sure. 2 to the power 6 is 64 or not? Is 2 times 2 times 2 is 8. 2 times 2 times 2 is 8. 8 times 8, 64. Okay, half is 32. 1/2 is 16, is not 18. Half of 32 is 16. So do you have resources to test the 16? Yes. So I can use 1/4 fractional factorial. But in this case, you need to define two defining relations. I will select I equal A, B, C, E. And we need to have one more defining relation, B, C, D, F. Can I write down this one as I equal A, B, C, E equal B, C, D, F? You can do it. So how do I select 1/4? Have a column A, B, C, E. Another column, multiply B times C times D times F. And select the 1/4 that A, B, C, E equal B, C, D, F, and all of them are pluses. And keep in your mind, if you select 2 defining relations, the third one will be defined automatically. The multiplication will be also positive, like A times B times C times D times B, this one times this one gave me A, D, E, F. So if you selected the 1/4, that this one is pluses, this one is pluses, also this one will be pluses. So and using this complete defining relation, you can find all the aliases. So the first step, if you work with 1/4, you select 1/2. So select I equal the highest order of an action, or I equal minus the highest order of an action, and use this defining relation to find all the aliases, and then estimate the ones at the left-hand side, and then go to normal probability plot, remove at least one, and then keep the others in the ANOVA table, test them at 5% significance level. If you are going to select one quarter, you need to define two defining relations, and the multiplication will be equal I also, and use this one to find all the aliases again. So multiply all of them by A. So A will be alias with B, C, E, will be alias with A, B, C, D, F, will be alias with D, E, F. I get rid of A if it is in the defining, I will add A if it's not. So it means if I estimated A using the average of pluses minus the average of minuses, it will be the same estimation of the interaction BCE. It will be the same value of the estimation of A, B, C, D, F. It will be the same estimation of D, E, F. Oh, all these ones will be confounded. All these ones will be confounded, will be the same, because you tested only 16 treatments out of 64 treatments. So everything has a price. You save much resources, but there are many effects will be confounded. So you keep finding all the aliases, and then you estimate only those guys, and then go to normal probability plot, or have normal probability plot, or Pareto plot, or reference plot, to remove at least one effect, because I need to save at least 1 degree freedom to estimate sigma square. And then you keep the others in the ANOVA table, and then find p-values and test the ones included in the ANOVA table. And don't forget to test the assumptions. So whatever you are working with, 1/2, 1/4, the first step, defining relation. Second step, the aliases. Third step, go to normal probability plot or have normal probability plot to remove at least one of these effects. And then keep the others in the ANOVA table. Then test the effects, test the assumptions. This is the main idea of fractional factorial. Any question?
Yes, I do have a
Sure.
question.
Sure.
So I think the part that I'm still confused about is how do we end up how do we end up creating multiple different defining relations that are all equal to each other?
See, you have go to the let's go to the design matrix. You need to have a column for A, column for B, column for C, column for D, column for E, column for F.
Right.
Minus, 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 plus, minus, 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 and so on to the last one, plus, 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 plus. Okay?
Yes.
And you decided to select 1/4, such that I will make I is confounded with A, B, C, E. You as a researcher, you select these kind of things.
Okay.
But do not select something like I is confounded with A. It is not something good, because you lose the main effect, will be confounded with the I, the estimation of mu, which is not good. But you can confound the mu, the overall mean, with some high interaction. Because most of the time, as a researcher, I do not interested in the highest order of interaction. So I can make it confounded with anything. So maybe I select as a researcher, I equal A, B, C, E. And also I will select I equal B, C, D, F. When you select the two defining relation, and then you select the treatments, which is this one is A, this one is 1, this one is A, then B, and so on to the last one, A, B, C, D, E, F. You select 16 treatments, 16 rows, such that the A, B, C, E is positive, B, C, D, F is positive, and by default, we'll find this one is positive. So you need to create a column for this one, column for this one, column for this one, and then you select the cases, select the rows that A, B, C, E is positive, B, C, D, F is positive, and A, D, E, F is positive. Select the first one, second one, third one, up to, you will find them, they are 16. Got it?
Yeah. Let's
This one, to understand this one, you need to do by hand. It's not by the R. I know we learned how to do by R.
yeah.
And one of the question in the homework, I asked you to do by hand or by R. I wish you do by hand. Actually, when I make the key answer, I made it by hand.
Okay.
So because when you do by hand, you understand what you are doing. But R, I know when you code in R, you understand, but doing by hand, it will make a difference.
No, I see. I think the main thing I was just confused about is that we ended up having 3 defining relations.
Yeah, because the you can work with only these two, but working with these two is the same thing like work with the third one, because the third one will be by default will be positive also.
خلاص بنمشيها يعني خلاص نمشي.
Okay.
توكل على الله يعني عندي
Any
97.
other questions? Any other question about fractional factorial? Okay, let me go to chapter 14. In chapter 14, we cover 2 designs, nested design and a split plot design. Let's cover the nested design. So what is nested design? In nested design, and why they have these 2 designs in one chapter, the nested design and split plot design? Because these 2 designs, most probably they have random effect treatments or random effect factors. So the nested design have some random effect and the split plot design have some random effect. So the nested design, you need to be familiar with the layout, the design. Let me explain the 2-stage nested design. Something like we have first treatment factor. Let's say this treatment factor has 3 levels, level 1, level 2, level 3. Let's say this is treatment factor A. And under each level, we have another treatment factor B. Let's say it has 3 levels also. So level 1, level 2, level 3. 1, 2, 3. 1, 2, 3. So why this one is not factorial design? Because I have 2 treatment factors, each has 3 levels. The difference between the nested design and the factorial design is this one. These 3 treatments or these 3 levels are completely different from these 3 levels. If they are the same, different from these 3 levels. If they are the same, it is factorial design in chapter 5. But these 3 levels under this one are different from these levels under this one, different from these 3 levels under this one. Because the levels of B get affected by the levels of A that is nested in. So this one is called nested design. And when we write down the statistical model, we need to show this kind of nested. So Yijk equal mu, the overall mean, tau I, the effect of the first treatment factor, beta j, the effect of the second treatment factor that is nested in the first treatment factor, plus the epsilon ijk. And I is 1, 2, 3 in our example. J is 1, 2, 3 in our example. K is the number of replicates. Maybe I will measure this one 2 times, measure this one 2 times, measure this one 2 times. To the last one, measure this one 2 times. So we have 2 replicates. So K is 1, 2. So when we write the statistical model is different from the factorial design. And also in the ANOVA table, you need to be familiar with, or you need to know, it should be given, which one is random, which one is fixed. So A is random or is fixed, B is random or is fixed. As I said, in nested design and split plot design are in only one chapter under chapter 14 because both have some random effect. Maybe A is fixed random, maybe B is random, maybe both of them are random. So I listed one of the lecture notes, one of the slides in the lecture note of chapter 14, part 1. I showed you that the ANOVA table, the values in the ANOVA table will be exactly the same, whatever, which one is random, which one is fixed. So if both of them are random, both of them are fixed, one is random and one is fixed, it doesn't affect how do you calculate the values in the ANOVA table. Like the values in the ANOVA table will be the same, like treatment factor A, treatment factor B within A, and then error, and then total, and then sum of squares, degree of freedom, mean sum square, mean sum square, and then F values, and then P values. Everything will be the same. It doesn't, the assumption about A and B are random or fixed, it doesn't change these values. The way I calculate these values is the same. But the only difference is what? These values are estimation of what? So I already, the same way you calculate the values, but the MSS is mean sum of squares. These values are estimation of what? Is based on the assumptions. If you assume A and B are fixed, so let's say this one is 1, this one is 2, this one is 3. If you assume A and B are fixed, the first value is MSE, and this is the estimation of sigma square. And the second value is MS due to B within A. This one is the estimation of sigma square plus the effect of factor B. Number 3 is which is MS due to A. This value is estimation of sigma square plus the effect of factor A. So when I look at these three equations, I see only one variance component, which is sigma square. Then the sigma square is MSE. But if you assumed A is fixed, A fixed, and B random, the number one value, the value number 1 is MSE, is the estimation of sigma square as before, but the others will be different. Like the value number 2, this one is the estimation of sigma square plus n, the number of replicates, times the estimation of beta square. The variability due to experimental error plus the number of replicates times the variability due to the differences among the treatment factor B. So far I have two variance components. The third value is the estimation of sigma square plus the effect plus n sigma beta square plus the effect of factor A. So when I look at these three equations, I see there are two variance components I need to estimate. I need to estimate sigma square and I need to estimate sigma beta square. The first one is easy. Sigma square hat is MSE. And now I can use this equation with this equation to find sigma beta square. It is number 1 minus number 2. This value minus this value divided by n. You get sigma beta square. If you assume both are random, A and B random, the value in the table, number 1 is the estimation of sigma square. Value number 2 is the estimation of sigma square plus n sigma beta square. Value number 3 is the estimation of sigma square plus n sigma beta square plus n b sigma tau square. When I look at these three equations, I see there are three variance components I need to estimate. I need to estimate the sigma square, easy. This one is MSE value, this equal number 1, the value number 1. And I use the equation 1 and 2 to find sigma beta square. I use the equation 2 and 3 to find sigma tau square. So we need to find these. And in the lecture note, everything is explained in details. The formula for sigma square, sigma beta square, sigma tau square is this one.
I have a
So,
quick question.
okay.
I'm really confused. So like, how come that if we were to say assume that A is fixed and B is random, the way to find number 3 is what is number 1 through number 3 when it comes to estimating the variance again? Because you're finding the mean squared error first, and then the mean squared error of the B factor dependent on whatever A was.
So, the
I'm having
equa-
I'm having a hard time interpreting this.
okay. You know these three values?
Yes.
These three values are estimation of what? It depends on the assumption about A and B. Because if the A is fixed, there is no variability due to A. I'm interested in testing the relevant levels are equal or not. But if A is random, I'm interested in the variability due to A is 0 or not. So the idea comes of the differences comes from what? Difference comes from there are some theoretical proofs for these values, because this course is applied course. So I can show you that the expected value of Q is this one is different based on the assumption of A and B. But this course is applied course. We do not cover theoretical.
Oh.
So,
Okay.
but if you wanted me to send you some documents that shows that the expectation of these values, I can do it.
Please do. I think
Okay,
I think that's how I'm gonna understand this better.
Okay, it's very simple, but I will send it to you.
Thank you.
You're welcome. So the only thing you need to know is when I give you a scenario, you need to know which one is random, which one is fixed. And then based on it is random or fixed, I will ask you to calculate the variance components, and you should know how many variance components in this example. Like if I said both of them are random, there are 3 variance components. B is random, A is fixed, 2 variance components, sigma square, sigma beta square. Both are fixed. There is only one variance component, which is the variability due to experimental error, which is sigma square, which is MSE.
Wait, so what happens if both effects are fixed?
If both are fixed,
Yeah.
if both are fixed, so we need to estimate sigma square only.
Okay. Wait, that makes sense.
Got it?
Sure.
And
Yeah.
then
Yeah.
you can use these p-values based on the assumption also. If the factor is fixed, for example, if A is fixed, you use this p-value to test mu A1 equal mu A2 equal mu A3 versus at least one is different.
Got
But
it.
if
Okay.
A is random, you use this p-value to test sigma tau square is 0 or not 0.
Oh,
Got it?
so if it's fixed, you check for the mean.
Very good.
If
And if it
it's
is random, you check the variability is 0 or no.
right. Okay. It's coming back. I see.
Okay. Any other questions?
Yeah, are we gonna have to calculate sigma squared or not?
What do you mean by calculating sigma square? It should be given in the ANOVA table.
Okay.
You don't need to use any formulas like the big formulas at the beginning of the semester. We do not use these formulas. I show you these formulas in the lecture notes, but we do not use them. We ask R to calculate it.
Okay.
Any other questions? Okay, the second design in chapter 4 is a split blood design. Split blood design. In a split blood design, you need to be familiar with the idea or the layout again. Why we use this split blood design, or when we should use this split blood design? If you have two treatment factors, A and B, but one of them is very hard to randomize and one is easy to randomize. In this case, you should use a split blood design. So how do I design my experiment? Because A is hard to randomize, B is easy to randomize. Let's assume A has 3 levels, like A1, A2, A3. And B has only 2 levels, like B1, B2. So how do, if both of them are easy, I will randomly assign the treatments, which is the combination between A and B. Like A1, B1, A1, B2, A2, B1, A2, B2, A3, B1, A3, B2. Those are the treatments. But one of them is hard to randomize, so I will not be able to randomize the combinations. So you need to randomly assign the hard one first and the easy one. And we covered, I think I gave you 2 examples in the lecture notes. For example, and in general, you randomly select one of the hard one first. Let's say A1. And then you prepare something, or like, for example, if I'm working with a big field, you select one big field, and then like in the example in the lecture notes, you select one big field, and then you randomly assign an irrigation method. And then the second treatment factor is fertilizer. So the first one is irrigation method, second one is fertilizer. This one is easy to randomize, this one is hard to randomize. So you assign, for example, irrigation method 1 to this field, and then you divide this field into 2 parts. One will be randomly assigned one of the fertilizers, maybe the second one, and then the other one will be randomly assigned one. And then you randomly assign another field, and then assign 1 levels of the hard to randomize, let's say A3 or irrigation method 3. And then you divide this one into 2 parts, randomly assign the easy one, like maybe B1, B2. And then select the third level of the hard to randomize. Let's say this one is A2. You divide into 2 parts, and then randomly assign the easy one, maybe B1, B2. Can I repeat it? Maybe, can I repeat the whole experiment? You can repeat the whole experiment one more time, and so on. So I use this method, or I use this design when one of the treatment factor levels are very hard to randomize, and I have another treatment factor, but its levels are easy to randomize. And when you write down the statistical model, you need to show this kind of a split design. When you write down the ANOVA components, you need to have the arrangement based on the split blood design. And when you find the T value, F values, P values, you need to be familiar with these kind of things. So, for example, is a statistical model. Yijk is mu plus tau I, the effect of the first treatment factor, plus beta j, let's say beta g is the replicate. I replicated the complete design 3 times or 4 times. Plus tau beta, the interaction between the first treatment factor and the replication. Plus gamma k, this is the second treatment factor. Plus all the interactions. Tau gamma I tau gamma is ik plus tau beta gamma jk plus tau beta gamma ijk plus epsilon ijk. So maybe you ask me, why do not have L? Because there is no, in this design, you will not be able to estimate sigma square. Something like is only one replicate. So, but I don't care because in ANOVA table, we will not divide by MSE, we'll divide by something else. So we don't need to estimate sigma square actually in the split plot design. And in the lecture note, I showed you the complete ANOVA table. You need to be familiar with which one is divided by which one and so on to find the F values and then P values. I will not make it complicated in the exam, don't worry.
I still have a hard time interpreting like the ANOVA table when it comes to the split plot design. So
Okay, go ahead.
yeah, I don't even know where to start, man. Just I'm confused. من فوق وتحت.
Okay, the idea is, because everything depends on the expected value of the sum of square, mean sum of squares. So the values in the mean sum of squares column are estimation of some specific linear combination of the effects. So you need, when you look at the expected value of the mean square, and then you think about, I would like to get some F value to estimate the main effect of A. So which one should be divided by which one? I should divide the MS due to A by what? You need to divide the MS due to A by some number that the difference between these two numbers is only the effect of A.
Okay. Yeah.
And then by the same idea, you can get all the F values to estimate the main effect of A, main effect of V, the interaction between A, B. But everything depends on the values in the column of MS are estimation of what? See my point?
I see. Yeah, so basically you're taking, yeah, I think I get it. Yeah.
Okay, good. And then don't forget the three assumptions: the constant variance, normality, and independence. We have all these three assumptions every time. And then we go to chapter 15. In chapter 15, we covered only one design, which is ANCOVA design.
I have a
Chapter
question about the
Sure.
split plot.
Sure.
So what does the tau beta gamma term represent?
Okay, tau, beta, gamma. Tau represent the first treatment factor, or you can use any notation, like the first one is the treatment factor effect, the first treatment factor effect. Second one is the replication effect. So you need to have first some effect for the first treatment factor, and some effect for the replicates. And then the interaction between these two, this is the order all the time. The first treatment factor effect, the replication effect, the interaction between the first treatment factor and replication, and then the second treatment factor effect, and the interaction between the replication and the second treatment factor, the first treatment factor and second treatment factor, and all of them, and then all of them, plus epsilon ij. You can use any notations. So for example, I can say this one is the effect of the replication, and this is the effect of the first treatment factor. And then the interaction between these two, and then I listed the second treatment factor, and the interaction between the second treatment factor and all the others, plus epsilon ijk.
Okay.
But this is the order in the statistical model, and also the order in the ANOVA table.
Okay.
Got it?
Yeah, thank you.
Yeah, welcome. Any other questions? Okay. The ANCOVA design. Again, you need to know when I should use ANCOVA design. You should use ANCOVA design if you have some explanatory variable or some confounding variable that I'm going to measure at the same time I measure the response. So you have, maybe you have A, B, C, minus, minus, plus, or whatever, and then you measure Y, and at the same time you measure X. So this is a new guy in this design. This is the guy makes the design ANCOVA design, or analysis of covariance design. Because when you measure Y, you measure at the same time X. So you can have this idea in the complete randomized design, complete randomized block design, Latin square design, Greek Latin square design, split plot design, repeated measure, any design. When you measure Y, you measure some explanatory variable or some confounding variable. But we worked with the confounding variable before as a blocking factor. I know. So the confounding variable can be used as a blocking factor. You measure some specific levels, or you select some specific levels, or select some blocks, and within each block you randomly assign the treatments. Or this is another way of blocking, another way of working with the confounding variable, that you measure the confounding variable when you are measuring the response. So when I write down the statistical model, whatever the statistical model, I will add beta X for this new guy. So the design can be complete randomized design. So it will be Yij equal mu plus tau I plus beta Ij plus epsilon Ij. The design can be complete randomized block design. So Yij equal mu plus tau I plus beta j plus beta ij plus epsilon ij can be complete randomized design with two treatment factors. So this is the first treatment factor, second treatment factor, plus tau beta ij, the interaction, plus beta ij. So this guy is the new guy that will be added to the model, whatever the model I'm working with, as beta ij, and so on. If this one is ijk, this one will be ijk. If this one is ijkl, this one will be ijkl, like this one also. So the ANCOVA model is something like blocking. In ANCOVA model, we block the confounding variable in a different way. In a way is different from the one we covered before in chapter 4, chapter 5, chapter 4, chapter 7, and so on. Rather than selecting some blocks, I'm going to measure the confounding variable. Once you measure the confounding variable, you need to modify the statistical model by adding this term. So, do we have requirements for ANCOVA? We have some requirements for ANCOVA. Requirements. 1, the relationship between X and Y should be linear. 2, the slope or the relationship between X and Y for each treatment is the same. Assuming we have 4 treatments, so X and Y for the first treatment is linear. Second treatment is linear. Third treatment is linear. And the slope is almost the same. Those are the two conditions or the two requirements for the ANCOVA design should be satisfied.
Can you please repeat the second requirement?
Okay, the second requirement, because I used beta, not beta I, it means all the treatments have the same slope. So this one, for all of them, the relationship is linear, but also for each will be almost the same for each treatment, because for each treatment I have some data. See my point?
Yes, thank you.
You're welcome. So these two requirements should be satisfied. If they are not satisfied, you need to go to the blocking, the one we covered before. Like if I have one treatment factor and one confounding variable, if you'd like to measure the confounding variable, this is ANCOVA. If you'd like to select some levels or some blocks for the confounding variable, you can work with the complete randomized block design. So which one I should work with, complete randomized block design or ANCOVA design? because in both I block the confounding variable. If the relationship is linear, either is fine. You can work with the blocking factor, the complete randomized block design, or you can work with the ANCOVA design. But if the relationship is not linear, it means if the requirements are not satisfied, you should work with the complete randomized block design. Do not work with ANCOVA. Do not work with ANCOVA unless the requirements are satisfied. Okay, so this is the idea of the ANCOVA. So you need also to be, familiar with the idea, you need to be familiar with the layout, you need to be familiar with the statistical model. You need to be familiar with testing, because in the ANOVA table, we will have one p-value for testing beta is 0 versus beta is not 0. And we have one more p-value to test mu H0, mu1 equal mu2 equal mu3 versus at least one is different. So one of the p-values for testing the confounding variable or the covariate has some impact on the response or not, but the others are as usual. And again, don't forget the 3 assumptions. You said there are some requirements. The requirements is different from the assumptions. The assumptions are the same again: independence, normality, and constant variance. Those 3 should be satisfied all the time. Any questions? Any questions?
Would it be possible to get maybe some more supplemental material for the split plot design in the chapter 15 ANCOVA model?
I can upload some examples with the answer, so you can go over it if you want.
Yes, I think that would be really appreciated, because
Okay,
I feel like,
I
yeah,
will take a note.
Yeah, I do agree. I do think that would help.
Okay, I will take a note and do it right away after I finish.
thank you.
Can you explain why you have the 2 different sets of hypotheses there next to p-value?
Okay, that's a good question. Let's go back to the statistical model. When you look at this statistical model, you have this one. This is the new guy. So we need to test this confounding variable has some impact on y or not by testing beta is 0 or not. If you fail to reject H0, it means this X, this confounding variable has no impact on Y. But if you rejected H0, it means this confounding variable has some impact on Y. This is a new guy, but the other p-values in the ANOVA table are like before. Like maybe I have three treatment factors, A, B, C. One is used to test mu 1 equal mu2 equal mu3 for the first treatment factor, another p-value for mu1 minus mu2 to the second treatment factor, or mu1 equal mu2 equal mu to the third treatment factor, and the interaction, and so on. So everything as before except this new guy. You will have one p-value for testing X has some impact on Y or not, but the others will be the same. Like for example, if I use this idea with the Latin square design. In Latin square design, we have two blocking factors and one treatment factor. So if I added the covariate, so I have one more X, I will have p-value for testing the first blocking factor is significant or not. One p-value for testing the second blocking factor is significant or not. One p-value to test the treatment factor is significant or not. And the fourth p-value will be for testing beta is 0 or not, beta is not 0. Got it?
Thank you.
Yeah, welcome. Any other questions? Okay, guys, I'm done for today. I will upload this review session, but give me some time because it take time to be uploaded. Okay,
Yeah. I would definitely maybe appreciate some more examples, but
I will.
otherwise, thank you, Professor.
you're welcome.
Thank you very much, Professor.
Thank
I
you.
appreciate
Thank
this.
you.
Thank
Thank
you.
you.
Thank you.
Take care.
Thank you, Professor.
Take care. Thank you.